Welcome to today's deep dive. We're looking at a pretty fascinating stack of sources you sent us today. I mean, it's a massive collection.
Oh, yeah, it really is. It ranges from these super dense, highly technical architectural white papers all the way to, some pretty aggressive industry op-eds.
Right, op-eds just fiercely debating the future of silicon. And just to set the ground rules as we dig into this material, we aren't taking sides here.
Exactly. No endorsements of the political or corporate viewpoints in these articles.
Yeah, our goal is strictly just to extract the core engineering arguments, figure out what is really going on behind the scenes. And just to anchor us in time, today is August 1st, 2026.
And the landscape painted by these sources right now is just, it's incredibly dramatic. Usually when we talk about open source technology, disrupting an industry.
It's if you're a tidal wave, right?
Mm-hmm.
Starts small, eventually washes away the old guard.
Right, like Linux. Linux dominating the server market is the classic example people bring up.
Yeah, and the numbers you highlighted in the research suggest that tidal wave has kind of already hit the semiconductor world. I mean, RISC-V, this open standard instruction set architecture, it's aggressively captured about 25% of the global chip market.
Which is huge.
It is a massive chunk of territory for something that was, an academic project not too long ago?
Yeah, it's an undeniable milestone. I mean, they have completely dominated the embedded space. We're talking microcontrollers, smart home devices, wearables, all of that.
But, and this is a big, but reading through the performance metrics in these white papers, it reveals a massive caveat.
Yeah, the high-end stuff.
Right. When you look up at the true peak of the mountain, like the death zone of the high-end domain flagship smartphones, heavy-duty cloud servers, supercomputers, Arrowmen, is still sitting comfortably on the throne.
They really are.
They're just sipping tea at the summit, while RISC-V is still trying to figure out how to set up base camp for that final ascent.
And you can feel the frustration in those op-eds you sent. It's really palpable. A lot of engineers and tech enthusiasts, they kind of bought into this narrative that an open standard would just naturally democratize every single tier of computing overnight.
And that is our mission for you today. We're going to unpack exactly why ARM maintains this iron grip on the high-end market, moving way past that simple, exhausted instruction set debate.
It's so much deeper than just the instruction set.
It really is. Okay, let's unpack this, because whether you are an analog IC designer or maybe a tech strategist prepping for a board meeting or just someone who loves understanding how our world is wired, the narrative that RISC-V is going to win the high end simply because it's open and free, it's a trap.
It is a total trap. And making business or engineering decisions based on that trap is incredibly dangerous right now.
Yeah.
To truly understand this rivalry, we have to analyze the billions of dollars ARM has spent on what your sources call accumulated optimization.
Accumulated optimization and ecosystem inertia. I love those terms.
Right. But to get that requires starting at the absolute foundational level of chip design. We have to talk about PPA.
PPA, power, performance, and area. Because if we're going to compare the heavyweights of the silicon world, we can't do it without speaking the language of the engineers who actually draw the blueprints.
Exactly. I mean, PPA is the absolute non-negotiable metric of the semiconductor industry. It's the designer's report card, basically.
Right.
Power is your energy consumption. So that dictates the battery life for a phone or, the massive cooling costs for a server farm. Performance is your speed, your clock frequency, data throughput.
And area is the physical die size of the chip itself, which directly controls your manufacturing costs and your defect rates, too.
Exactly.
Reminds me of the old project management triangle, right? Good, fast, cheap. Pick two. You push one corner, the other two get pulled entirely out of whack.
That's a great way to look at it.
But I do have to push back here for a second, especially looking at the notes we got from the analog design community. Like, isn't PPA primarily a digital engineer's metric? Like, if you are an analog designer, say you're working on a radio frequency block or a complex sensor interface, you just need to hit your bandwidth specs. You hit the required speed and your job is done right.
What's fascinating here is that this is exactly the misconception holding a lot of engineers back from becoming true system-level strategists.
Oh, really?
Yeah. In analog design, PPA isn't just some automated output you get from a software simulation tool. It's actually about the fundamental intent of your entire design.
The intent. Okay, I'm going to need you to break that down.
Sure. So a top-tier analog engineer does not just hit a speed specification and call it a day. They look at the entire system's PPA budget.
Right.
They actively calculate how to, say, choose a completely different circuit topology to reduce their physical area by 5%. They maintain the required performance, but they intentionally allow a 10% power increase.
Wait, why would they allow a power increase on purpose?
They make that specific compromise because they know the digital side of the chip is currently coming in under its power budget. It is a highly negotiated, system-wide trade-off.
Oh, wow. So they're playing a team sport with the silicon real estate rather than just optimizing their own little isolated island.
Precisely. And in 2026, the metrics detailed in these architectural papers have evolved into something even more brutal. The industry has moved to PPAC.
Right, adding cost into the equation.
Yeah, because this accounts for advanced packaging and testing costs that the raw silicon area alone just doesn't capture anymore.
Because we're stacking chiplets now. It's not just one flat piece of silicon. It's literally a three-dimensional puzzle.
Exactly. Which introduces PPE, adding thermal limits. Stacking incredibly dense transistors on top of each other creates a scenario where heat density is hitting a literal physical wall.
You are essentially wrapping hot engines in thick blankets.
That's exactly what it is. And finally, there's PPITSect, adding time to market. Because the most beautiful, perfectly optimized chip architecture is completely worthless if it hits the market 6 months after a competitor's product.
So applying this incredibly strict multi-dimensional PPA scorecard to the rivalry really reframes the whole conversation. ARM's flagship cores, like the Cortex-X series for phones and the Neoverse series for servers, they aren't just sitting on a mountain of cash.
No, not at all.
They're sitting on decades of brutal, iterative physical testing.
Decades of accumulated trial and error. I mean, to achieve their current PPA scores, ARM has optimized deeply complex mechanisms. Take out-of-order execution, for example.
All right.
Instead of a CPU processing a list of instructions in strict sequence, like a chef waiting for water to boil before even starting to chop vegetables, the chip looks ahead. It identifies resources that are free and processes future instructions out of order.
So keeping the kitchen completely busy at all times to maximize throughput.
Exactly. They have also refined branch prediction to an absolute art form. When a computer program has an if-then choice, the CPU doesn't wait to find out the answer.
Right, it guesses.
It guesses which path the code will take and starts executing it early to maintain momentum. If it guesses wrong, it throws the work away. But ARM's guessing accuracy is astronomically high. Every single generation of ARM chips has squeezed the PPA sponge tighter by perfecting these microscopic physical mechanisms.
Meanwhile, the open source white papers we were looking at, they show RISC-V with these frankly gorgeous, highly modular specifications on a whiteboard.
Yes.
But a specification isn't silicon. You were saying RISC-V fundamentally lacks that battle-tested PPA stability when you throw completely unpredictable real-world workloads at it.
Yeah, having a brilliant microarchitecture on paper or running it in a software simulator, that is only step one. The gap between a theoretical architecture and a physical chip that perfectly balances power, performance, and area under chaotic, real-world thermal conditions. It's a chasm.
And ARM crossed it years ago.
Right.
Yeah.
RISC-V is still building the bridge for high-end applications.
Because a perfect whiteboard design is completely useless if a foundry can't efficiently print it onto a silicon wafer. Reading through the manufacturing sections of these sources, this feels like ARM's most heavily fortified barrier. Let's talk about physical implementation.
Yeah, the manufacturing moat is arguably the most underappreciated advantage in this entire rivalry.
The sources heavily reference something called a POP, and not the music genre, obviously. The processor optimization pack. ARM doesn't just email you a blueprint and wish you good luck.
Definitely not. They work intimately with the big foundries like TSMC, Samsung, Intel, long before a chip designer ever even licenses the core.
The way these white papers describe it, buying a high-end ARM core with a POP is like buying a premium, pre-assembled IKEA cabinet that has been laser cut specifically for TSMC's 3nm or 2nm manufacturing node.
That's a really good analogy.
The holes are pre-drilled, the hardware is sorted, it just fits perfectly into that specific factory's process. Whereas licensing a high-end RISC-V core is like someone handing you a beautiful schematic, pointing to a dense forest and saying, go chop down the wood, mill it yourself, and verify every single joint.
That perfectly captures the time-to-market aspect of PPACT we talked about. With ARM, that pre-drilled assurance drastically reduces the time engineers spend physically verifying that the chip won't fail when manufactured.
Which is critical.
In the high-end space, product cycles are ruthless. A 6-month delay kills a smartphone launch. But the challenge extends far beyond the core processor itself. We have to consider the entire neighborhood around it.
Oh, the peripheral IP. The other essential components that make up the system on chip.
Right. A high-end SAW is like a bustling metropolis. The CPU core needs high-speed memory controllers to fetch data. It needs PCIe Gen 6 interfaces to talk to external components like graphics cards.
And it requires coherent interconnects, right? Like ARM's CMN series.
Exactly, to act as a massive neural highway, keeping dozens of different cores perfectly synchronized without data collisions. ARM licenses this entire metropolis as a pre-verified, tightly coupled package.
It is basically a gated community where all the plumbing and electrical wiring is legally guaranteed to work together out of the box. But if you take the RISC-V route,
Then you are stepping into the role of a general contractor. You have to license a PCIe controller from vendor A, a memory controller from vendor B, and stitch them all together with your RISC-V core.
which sounds incredibly complicated.
It is, and the critical issue is that the integration risk falls entirely on you. If a severe latency bottleneck emerges between the RISC-V core and the third-party memory controller during physical testing, no one is coming to save you. You have to debug the interaction yourself.
Man, that is a terrifying amount of financial risk for a flagship product. And hardware is only half the battle, too. Several of the op-eds focus heavily on the software ecosystem, which seems to be where the open and free dream takes its hardest beating. There is a structural difference between a CPU technically executing a program and running that program optimally.
Hardware purists often have a pretty big blind spot here. They design a blistering fast chip and just assume the software developers will naturally flock to utilize it. But the software ecosystem possesses incredible inertia.
Yeah.
We have to examine compilers like LLVM or GCC. These are the crucial translators that take human-written code like C++ or Rust and translate it into the specific machine instructions a processor understands.
And those translators have known ARM intimately for over a decade. They understand all of ARM's weird local slang, its pipeline depth, its specific memory latency behaviors.
That's correct.
The compiler automatically arranges the machine code to squeeze out an extra 1% of performance here, a 0.5% there.
The compilers have been aggressively tuned by thousands of developers to exploit every hidden microarchitectural advantage ARM possesses. RISC-V compiler optimization is improving rapidly, but it's still relatively immature for massive, highly complex, high-end server workloads. The translator doesn't know the best way to phrase things yet.
And that inefficiency multiplies when we move up the stack to runtime environments, right? Things like Java's JVM or JavaScript's V8 engine, which power massive swaths of the global web and enterprise software infrastructure.
Right.
Even today, in 2026, the benchmarks in these sources show that if you put a top-tier RISC-V server next to an ARM server with identical theoretical hardware capabilities, the RISC-V machine often suffers a 10 to 20% performance penalty.
Purely because the software engine isn't heavily optimized for its architecture yet. We also have to confront the double-edged sword of RISC-V's defining feature, which is its modularity.
Right, the modular.
The architecture allows designers to snap together different standard extensions. You can add a specific vector math module or a specialized cryptography module, tailoring the chip perfectly to a task, which is brilliant for custom embedded devices.
But the software developers in these sources argue that modularity is actually a nightmare for a standardized ecosystem.
It really is. ARM v9, the current flagship architecture standard, is highly prescriptive. It dictates a very specific, uniform baseline of hardware features.
So when an operating system developer or an app creator compiles their software for ARM v9, they know exactly what capabilities will physically be there.
Exactly. But RISC-V's modularity naturally creates fragmentation. It becomes incredibly difficult to heavily optimize a general-purpose operating system when the underlying hardware extensions can vary wildly from one RISC-V chip to the next.
Okay, so we have established the unforgiving rules of this arena. PPA is the ultimate judge. ARM has the foundry fast track with POP, and the software ecosystem has a decade of entrenched bias. Here's where it gets really interesting. What happens when we put the actual silicon heavyweights of 2026 into the ring? The teardowns you provided give us a fascinating look at the contenders.
It is the most competitive lineup the industry has seen in years, honestly.
Okay, so in the blue corner wearing the crown, we have the king, the ARM Cortex X925 for mobile, and its server sibling, the Neoverse V3. These architectures are absolute monsters.
Total monster.
The documentation highlights a 10-wide decode engine. I want to unpack that because it sounds intimidating, but it is fundamentally about how much data the chip can swallow at once, right?
Think of it like a highway toll plaza. A standard processor might have 4 toll booths open, processing 4 cars or instructions simultaneously. ARM has engineered a 10-wide plaza.
Wow.
They can ingest, decode, and route a massive amount of instructions simultaneously. This pushes their clock speeds well over 4.0 gigahertz. When it comes to flawless, single-threaded performance, they just dominate the benchmarks.
They are the culmination of all the accumulated optimization we just discussed. But the white papers outline a severe catch. Building a 10-wide toll plaza requires a massive amount of physical land.
Yep, that hurts your area metric in PPA.
Right. They draw immense power. They carry massive licensing royalties.
Yeah.
And perhaps most importantly for innovators, they are a complete black box.
Exactly.
ARM dictates the exact layout. You cannot pry open the engine and add your own custom hardware instructions to the core.
You are renting ARM's perfection, but you must play strictly by their rules.
Which brings us to the red corner, the ARM killer, the 10-storent Ascalon X.
Yeah.
This design has serious pedigree. It was built from scratch by Jim Keller's team, the same architect behind Apple's M1 and AMD's Zen Revival. Ascalon X is an 8-wide decode architecture, hitting over 21 SPSUN per gigahertz.
Which is incredible.
And just to clarify that metric for a moment, SPSUN is basically a standardized decathlon score for integer math, proving this chip handles heavy general-purpose logic incredibly well.
It proves they aren't just good on paper. They are targeting the exact heavy workloads ARM dominates.
Right. And Ascalon X also packs a massive 2 by 256-bit vector unit using the RISC-V standard. A vector unit is what allows a chip to perform a single mathematical command on a massive array of numbers simultaneously.
Like loading 256 boxes onto one giant truck instead of making 256 individual trips.
Exactly. On paper, this design looks capable of beating ARM's vector extensions in AI inference tasks.
The engineering really is breathtaking. But evaluating it through our PPA and ecosystem lens, the trade-offs become pretty clear.
Yeah, the primary trade-off is the track record. It lacks the decades of real-world silicon verification that ARM has accumulated. It does not come with ARM's TSMC POP ease of use.
Right. Choosing Ascalon X means taking on significant physical implementation risk and tackling the software integration yourself.
To complete the picture, though, we have to look at the pragmatic alternative. Rounding out the ring, we have the honor student, the C5 Performance P870. The teardowns show a 6-wide core, running around 3.0 gigahertz. It is an early adopter of the RVA23 standard, which is the RISC-V community's organized effort to fix the software fragmentation issue by establishing a uniform baseline.
Which is a big step.
It is heavily verified and highly reliable. But its performance metrics really only rival older ARM generations, like the Cortex-X2 or X3. It is fundamentally a safe bet, but it is 1 or 2 generations behind ARM's bleeding edge.
It serves the designer who desperately wants to use RISC-V without bleeding on the cutting edge of unproven silicon.
Okay, I am looking at all this data, and I just have to ask a strategic question.
Go for it.
If I am a system architect building a highly specialized next-generation AI accelerator or an advanced automotive computer, the Ascalon X looks like a monster. If the vector units can beat ARM at AI inference, why wouldn't I just take the leap, eat the integration risk, and use it?
If we connect this to the bigger picture, you are hitting on the exact pivot point of the entire semiconductor industry right now. If your goal is to build a general-purpose smartphone chip or a standard cloud server running standard operating systems, choosing RISC-V right now is a massive gamble.
Okay.
The software wall is too thick and the physical implementation hurdles are too high. ARM's cohesive, pre-verified package is overwhelmingly compelling.
Because you need every general-purpose app to work flawlessly the exact moment the user turns the device on.
Exactly. However, if you are building an AI accelerator, a radar processing unit for an autonomous car, or utilizing a chiplet architecture where you are snapping distinct specialized pieces of silicon together.
Ascalon X is incredible.
Yes, in those specific domains, you desperately need to escape ARM's black box.
So what does this all mean? Distilling this massive stack of sources. If you are sitting in a strategy meeting tomorrow, pitching RISC-V to your engineering team or a client, you absolutely cannot use the lazy argument that it is open, free, and therefore better.
No, absolutely not.
In the high-end space, freedom equals the massive, expensive responsibility of physical verification and software optimization.
The strategically sound, mathematically justifiable reason to adopt a high-end RISC-V core is to create a strategic differentiator. You use it to build something ARM literally forbids.
The sources mention custom instructions. Give me a concrete example of a strategic differentiator in action.
Let's return to our analog designer working on a proprietary signal processing circuit for a new radar system.
Okay.
If they use ARM, they must funnel all their analog data through standard interfaces, process it using ARM's generic instruction set, and just accept the resulting latency.
Right.
With RISC-V, that designer can crack open the microarchitecture. They can write a custom instruction that physically wires their proprietary analog circuit directly into the processor's execution pipeline.
Oh, wow.
Yeah, they can create a hardware shortcut that executes their specific radar algorithm 10 times faster at a fraction of the power budget. ARM does not legally or technically allow you to alter their core pipeline like that.
So you are taking on the heavy burden of verification. But the payoff is a final product that your competitors literally cannot replicate using off-the-shelf ARM cores. You are changing the rules of the physics to favor your exact workload.
You step out of the general purpose race entirely and build a hyper-optimized machine.
That shift in perspective really brings the whole debate into focus. But as we wrap up, there was one final thread from the research I want to leave you, our listener, to mull over as you watch the tech landscape evolve through the late 2020s. We talked earlier about PPAT, how thermal density is becoming a literal physical wall.
Yeah, heat dissipation is rapidly becoming the primary bottleneck for continuous performance scaling. The energy density of modern chips is just staggering right now.
Right now, ARM relies on these massive, power-hungry 10-wide decode cores to maintain their absolute dominance in single-threaded performance. They are pushing the silicon layout as hard as the physics of cooling will allow.
Right.
But as we push deeper toward 2030, will that extreme heat generation, that massive thermal footprint, eventually become ARM's Achilles heel?
It is a critical vulnerability. I mean, as transistors get smaller, extracting the heat becomes exponentially harder.
Will the sheer physics of cooling these ARM behemoths give the leaner, highly customizable RISC-V chiplets the ultimate backdoor to taking over the high-end market? Not by beating ARM in a straight, general-purpose sprint, but by outmaneuvering them when the physical environment gets too hot to handle.
It is a really fascinating problem to watch unfold.
We want to thank you for joining us on this deep dive and sharing these incredible sources. The next time you see a headline hyping up an open-source hardware revolution, we hope you view it through the unforgiving lens of a strict PPA budget. In the high-end silicon arena, there are no free lunches, just deeply complex engineering trade-offs. Keep analyzing, keep questioning, and we'll see you on the next deep dive.